Much of the next three lessons are going to be a review, especially if you've taken an introductory course in physics and you've looked at energy and the conservation of energy. What we're going to begin with is work. I always like starting with work and looking at what it's all about. Work is basically the transfer of energy. It's done when a force acts on an object, causing the object to move in the direction of the force. Okay? So here we've got force applied over a distance. With impulse, we had force applied for a time. Work is a little bit different than impulse. It is not a vector. Work is, of course, a scalar quantity, and it's represented by the dot product of two vectors. Okay, so we took a look at a couple of ways that we could do the dot product. Work is, of course, a scalar unit. It is not a vector. So when we take the dot product, this is one of the ways of multiplying two vectors out. It has units of Newton meters, and we have a derived unit for Newton meters, and that's the joule. So here's an example. Let's calculate the work that's done by these two situations. Applying a force of 20 newtons right to a 0.5 kilogram puck as it slides along a frictionless surface from rest to 10 meters per second in 0.2 seconds. And in part B, let's lift a 57 kilogram outboard motor for a distance of 1.4 meters from the ground up to the box of a pickup truck. All right, in part A, we've got a force. It's applied to a mass for a certain amount of time, and it picks up some velocity. Okay, so what's going on here? Well, first of all, if we want to calculate work, we need to know the distance over which this was pushed. So let's calculate what this distance is, or what this displacement is. And we get 1/2 times 10 times 0.2. Okay, it's pushed for a displacement of a meter. Now we can go and we can say, okay, work is equal to force dot displacement. And we can calculate 20 newtons for a total of 1 meter. It gives us 20 joules. Okay? So that's a very standard example of work, basically transferring energy from one type of energy, basically the energy that's associated with your muscles, and we're applying this force and we're turning it into another type of energy, the energy that's associated with speed, and that's kinetic energy. Okay, in part B, we're lifting a 57 kilogram outboard motor a distance of 1.4 meters from the ground up to the box of a pickup truck. So we have displacement and we have mass. But if we're lifting an outboard motor, we have to talk about the force that we're using here. So when you lift something from the ground up to a certain height, you have to work against some force. And of course, you would be right if you said, oh, that's the force of gravity. And that's exactly what we're going to do to calculate how much work we have to do to lift this motor. We have to use the force of gravity. So what force is it? Well, it's going to be gravity. And we know that the force of gravity, for our intents and purposes, is mg. So here we've got mg dot with our displacement. And if we take those things, we calculate 782.04 joules. And what that gives us is 7.8 times 10 to the 2 joules in correct scientific notation, or significant figures. The one thing we should say is, hey, how come we didn't worry about vector directions and all of this? Vector directions, especially when we're talking about one dimension, and we're doing a dot product of two things that are either parallel or anti-parallel with each other, give us a maximum. That goes back to the definition of the dot product that we looked at earlier. So let's take a look at maybe when we need to have an angled force that's acting here, and we got to use the dot product a little bit. All right, so first of all, we got a horse and it's pulling a sleigh. But it's not pulling it exactly horizontally. It's using 100 newtons, and it's pulling at an angle of 30 degrees above the ground. Okay, so like this. The sleigh moves 30 meters across a horizontal ice surface. There's no friction that's acting. How much work is the horse doing? Well, in this case, it makes sense to talk about this dot product and what work is all about. Because if work is force dotted with displacement, we had a definition for what the dot product was earlier. And we can say here, the reason that this is going to be a dot product rule is because there's only one component of this force, this 100 Newton force, that's going to actually pull the sleigh along. This component, the Y component, doesn't actually help to move the sleigh in the X direction. It just kind of cuts down on the normal force that's on the sleigh. This is the only component of the force that's important. So watch what happens. When I look at my displacement, is 30 meters in the I hat direction and no meters in the J hat direction. The sleigh doesn't move up or down. The force, on the other hand, is 100 cos 30 I hat plus 100 sine 30 J hat, which is 86.6 I hat plus 50 J hat. And watch what happens when I take the dot product of this. Basically, I know that the 86.6 I hat is multiplied by the 30 I hat over here. And what I get is 86.6 times 30 plus the 50, which would be dotted with or multiplied by 0 because we dot the J hats and we dot the I hats and we add them up. But this 50 times 0 is just 0. So basically what that's telling us is that all of this force, this 50 newtons in the J hat direction, is wasted because it doesn't move, it doesn't do any work on the sleigh. This whole force here in the J direction does nothing because it doesn't move it anywhere. Everything comes from the I hat component of the force, and we get 2,598 joules. Okay, and that's your final answer. Now, let's go on. It's not that we're going to change this or we're going to do this any different, but we did have a definition for the dot product, and it's important that we talk about it now. So using algebraic vectors, we know the dot product took care of resolving force and displacement into its proper components. And it only calculated the amount of force acting in the direction of the displacement. But there's an alternate method that we can take, and it's better to understand the dot product and what it's all about. That's far superior. But we can also introduce this little formula down here that looks at the angle in between two vectors and kind of does the work for us. Now be cautious. You never want to just take an equation and plug things into it. You want to understand why things are happening the way they are. The definition of the dot product is U dot V is equal to the magnitude of U times the magnitude of V times the angle in between, times the cosine of the angle in between them. And we can apply that to our definition of work. So we take the magnitude of the force and the magnitude of the displacement, and we multiply by cosine of the angle in between them. Okay? So really what we've done is we've completely eliminated the need to look at vectors by applying this little formula. And sometimes this can be helpful. A newspaper carrier pulls a wagon with a force of 275 newtons at an angle of 45 degrees to the horizontal. How much work is required to move the wagon 8 meters? So again, this is a review of grade 11, but here we got 275 newtons pulling up. We got a displacement of 8 meters in this direction, and we have an angle of 45 meters in between those two vectors. Hey, might be a good time to use our definition of the dot product for work, which is FD cos theta. We can substitute our values in, and we get 1,555.6 joules, and we correct for significant figures. So this is an alternate method, but just to make sure you understand, use an algebraic vector method to arrive at the same answer. Because again, this force, which is directed at 45 degrees, there's only one component of this force that does any work. And the dot product shows you that, of course, when the displacement has 0 I hat direction, any I hat unit of force is going to be wasted. It's wasted force because it doesn't do anything to help move this along. Okay? So try this using an algebraic vector method, and you'll arrive at the same answer. Let's talk about work that's done by friction, because friction also does work. But its action, however, is to remove energy from a system. Okay? So we call friction a non-conservative force. And Because this is a grade 12 course in physics, we would like to continue to use the conservation of energy, but it's complete. It's incomplete and incorrect if we don't consider friction, because everything else that we can do by Newton's laws includes friction. So why wouldn't we include friction in our discussion of energy and the conservation of energy? So this is the next level of sophistication when we start talking about energy, is that we're going to start considering some of these non-conservative forces. And a non-conservative force is one that, well, it kind of depends on the path of that the object takes. So here's a pretty good example. A 6 kilogram block is pulled to the right along a horizontal surface with a coefficient of friction of 0.15. We're using a horizontal force of 12 newtons, and we're pulling it for a distance of 3 meters. How much energy has been transferred to the block over this distance? So the force that we're using is going to basically do work. And friction, well, it's going to do work too, but it's going to do negative work. So our block is going to pick up some energy from the work that we do, but it's going to lose some energy from the work that friction does. And we'd like to know what that balance is. So here's what we know. We know that the mass is 6 kilograms. We know that mu is 0.15. We know that our applied force is 12 newtons. And we know that the displacement over which we're going to move this block is 3 meters. Let's draw a free body diagram. And here it is, basically looking from the side. We got gravity down, we got the normal up, because it's over a surface. We got the applied force, and we've got this force of friction acting in a motion that's opposite to our applied force, acting in a direction that's opposite to our applied force. This is pretty standard, and my gut would tell me you would know how to do this kind of free body diagram on your own. Work then, the total amount of work that's done on this block is going to be the work that it gets from the force that's applied, and we're going to subtract the work that friction does, and that's going to provide us with the total amount of work. So how much work does it get from the applied force? Well, applied force times the displacement, dot the displacement, minus the force of friction dotted with the displacement. Okay? Really, this is the sum of the forces dotted with the displacement. Okay, F net dot D. Force of friction, we know, is mu times the normal. And in this case, the normal happens to have the same magnitude as the force of gravity because it's a horizontal surface. We can take this and plug it in here, and here's what we get. 12 times 3, which is force times displacement, minus 0.15 times 6 times 9.8 times 3. And when we calculate this, we get 9.5 joules of energy that's been transferred to the block. So again, our force has provided energy to the block, the force of friction has taken energy from the block, and this is the trade-off that we get, almost 10 joules.